Hudson. So Dr. Aaron Hudson is an assistant professor at the Fred Hutch and former graduate student from this department. He's engaged in the design and analysis of vaccine efficacy trials. He develops and employs statistical tools to analyze a person's immune response to vaccination and to assess the risk of adverse health outcomes. His methods involve the use of advanced computational techniques, including machine learning, to draw inference from data commonly generated from studies involving large populations comprising many different groups of people. Aaron, it's a great pleasure to have you. We look forward to your talk.
Yeah, great. Thanks for having me. And it's nice to be able to finally be able to give a seminar in my home department after a while. For folks maybe tuning in online or here who saw my talk at the Hutch yesterday, I'm going to be talking about the same material from two fairly different perspectives. So I hope I don't bore you too much, but these talks are pretty complementary. Second, I was pretty ambitious with the amount of material I tried to get in, so it might be a little bit dense. So do please stop and ask me questions if things are unclear, and I'm happy to do so. And so with that, I'm going to just get right into things. With that, I'm going to get just right into things. Great. And so just an outline for me to keep myself organized a little bit. So first, I'm going to provide a brief introduction where I talk about what kind of inference problem we'll be discussing today and why it's relevant. Second, I'll give a brief review of what do and don't we know about this problem. So what methods are available for estimation and inference and what are the limitations. And then I'm going to talk about our new proposal for addressing this problem and a brief demonstration, simulations, and some concluding remarks at the end. And so in this talk, I'm actually going to spend 75% of it or so on the first two items. And I'm only going to have about 5 slides or so on my proposal. Reason for that will hopefully be fairly obvious, but this is a sort of problem where establishing relevance is important and explaining why the problem is a problem is also important. But then the solution ends up following pretty naturally after we understand the problem well. So starting with relevance. So a lot of my work has to do with performing statistical inference on parameters that take the form of a function. And I'm interested in these because these are of interest in many practical applications. So for example, in many settings, we're interested in performing inference on something like a regression function. Say we're interested in studying the relationship between some predictor or some exposure and some outcome. And we want to do this by studying the conditional mean on the outcome given the exposure, which might be continuous. And so we can frame this science problem as an inference problem where we're interested in this function valued statistical parameter. Similarly, so before I started working on all this stuff, I started thinking about graphical models first. So we might be thinking about, we have 2 different random variables, say gene expression levels or some sort of biomarkers. And we want to understand how and whether these 2 variables are correlated or associated in any sense. In other words, are they jointly dependent or something like that? And so in this case, we might be interested in just studying the joint density of this pair of variables. Okay. So to formulate the specific problem I'm going to be answering, we're going to be performing a comparison between 2 different models for the parameter of interest. And I'll just say that we have a full model for the parameter of interest, which is going to contain all different plausible values that the parameter could take. And then a reduced model, which is going to contain a subset thereof. And our question that we're going to be answering is the full model better than the reduced model or just as good in some sense? And so to think about just as good, we can define a goodness of fit criterion for the parameter of interest. So for example, in regression problems, we can assess how well a regression function is doing by looking at something like an expected prediction error. Or similarly, if we're looking at how well a density function is fitting the data, we can look at something like an expected log likelihood or an entropy, depending on who you ask, to the same thing. And so we can say that our target parameter is getting inference on, our target function is then going to be defined as the best fit in the full class. And then we're wondering whether we can get just as good of a fit if we're looking in the reduced function class. Okay. And so it's helpful at this point for me to start formalizing things. And so I'll say that I have random vectors, z1 through zn, and we're interested in any function value parameter theta naught, which can be a conditional mean or a density or anything else. And we want to use these random observations to make inference about the parameter of interest. So we'll say that we'll assume that theta naught resides within some large function class theta. And we'll define some goodness of fit measure that's a map from any function within this large function class theta to some value, which will measure how well our parameters fitting. And so we'll say that lower values of G of theta are going to indicate a better fit. And so the best parameter is going to be the thing that minimizes the goodness. So we're going to assume that our parameter of interest theta naught satisfies that it is the best fit among all functions within our function class with respect to the goodness of fit criterion. And similarly, we're going to consider some reduced model, which we'll denote by theta star, and we'll define theta star in 0 as the minimizer over the reduced class. And so our target statistical parameter is going to be the difference in the goodness of fit measures. So the goodness of fit over the reduced class minus the goodness of fit in the full class. So how much better do we do by using the full class compared to the reduced class? Okay. And throughout, I'm going to call this target parameter the improvement in fit. Now, one thing that we can see immediately is that this parameter of interest size 0 is non-negative. So it's a measure of dissimilarity between theta naught and theta star, and it's a non-negative measure of dissimilarity, which is going to be really important, and we'll get into why that's important later. And we're interested in the null hypothesis primarily of no improvement in fit, so that size 0 is equal to 0. So I can start then by introducing a few examples of ones that might be interesting or helpful. So revisiting the regression problem, we can think of our data taking the form Z is equal to W and X and Y, where Y is our outcome. X is a subvector of predictors of interest, and X and W is a vector of covariate adjustments that we might like to use. And then the question that we're asking is whether X is conditionally associated, the predictor of interest, X is conditionally associated with the outcome Y, conditional upon the adjustments W. So as I stated before, a natural way that we often do look at this is we'll want to make inference on the conditional mean. So here we'll define our target function of interest, theta naught of W and X, as the conditional mean of the outcome, given both the exposures and the predictor of interest X and the adjustments W. And we're going to consider two different models for fitting the conditional mean. So the first model, the full model, is going to contain all functions that can both change with the predictor of interest and with the adjustments. And we're going to compare that with a reduced model that only contains functions that depend on W, but does not contain any functions that depend on X. Okay. And so for this kind of parameter, as I mentioned before, we can define a goodness of fit as something like a prediction error. So in this case, it's an expected squared error loss. So on average, how far is our outcome away from our prediction function? And we're asking whether the reduced or the full model is achieving a better prediction error. And so you can show that when your full function class is big enough, that the full and reduced best fits are equal to, respectively. The full one is the conditional mean of the outcome given both the exposure and the adjustments, and over the reduced model, it's just the conditional mean of the outcome given the adjustments. And moreover, you can show that the parameter of interest, this difference in goodness fit or the improvement of fit, is only equal to 0 when the two conditional means are equal. So this provides you a natural way of assisted conditional dependence, meaning that the conditional mean may or may not depend on the predictor of interest. And so another problem that I think is fairly canonical is that, again, we want to assess marginal independence between two one-dimensional random variables here, which I'll denote by U and V. And we can frame this as a comparison of two different models for the joint density of U and V. So basic probability laws tell us that U and V are only dependent when the joint density is equal to the product of the marginal densities. So now we can compare two function classes, where the first one is the full collection of all possible bivariate density functions, and the second is all bivariate density functions that can be expressed as the product of two different marginal density functions. Right, and so you can measure the goodness of fit of any density function, as I mentioned before, using something like the expected log likelihood, which is also called the entropy, depending on who you ask. And you can, in this way, obtain a notion of improvement of fit. That's the difference in the expected log likelihood between the full and reduced class, which is known as the mutual information, and is often considered as a target of interest in the graphical modeling literature. And so in the previous two examples, I considered two specific kinds of parameters, but this sort of framework really works more broadly. So here we'll just say that theta naught is any parameter. So it can be, say, a density function or a regression function or a hazard function or whatever you might be interested in. And we'll just say for simplicity that we want to compare our function theta naught with any fixed function that also resides in theta. So a full model is just a big model of functions, a big class of functions for theta naught. And our reduced model is just going to be a singleton set just containing a single fixed function. So a very silly way, but reasonable way to measure goodness of fit is just to take an integrated squared difference between the true parameter and any candidate null parameter. Obviously, that's minimized at the truth because then the integrated squared difference would be 0. And so that means that this can also be viewed as a goodness and fit parameter, this integrated squared difference between the truth and the null. And so this also fits within our framework. So this means that our framework is generally useful for inference on function value parameters. And so our primary objective today is going to be to assess whether the improvement in fit is 0. So there's a difference of goodness fit over the best class or over the reduced class equals 0. And additionally, we're going to want an estimator for the improvement in fit. And we want to do this under weak model assumptions, and we want to allow for our full function class to potentially be large. And first, I'm going to talk, before I get into my contribution, I'm going to talk at length about an existing approach, also worked on a lot at University of Washington in-house, and talk about what it does well and what it doesn't do so well. And so one approach goes essentially as follows. So the first thing that you'll do is you'll estimate the goodness of fit or construct an estimator for the goodness of fit at any different fixed theta within your function class. Second, you'll then construct estimators for theta naught and theta star by minimizing the goodness and fit over the reduced and full function classes. And then third, you'll take your estimator for the improvement in fit as the plugin. So you're comparing the empirical estimators with the empirical goodness of fit over the full and reduced class. So just a plugin. And then we'll talk about what does and does not go well here. So first, just a little assumption. So we're going to assume that our goodness of fit, the parameter, is nice, meaning that it resembles a population average. And when a parameter is nice, the technical phrase would be pathwise differentiable, but for now I'll just say nice. When a parameter is nice, that means that we can construct estimators that behave like sample averages. And because sample averages behave nicely, this is a reasonable starting point for performing inference. So to be slightly more formal, because the goodness and fit is a population average, it's possible to construct an estimator such that the difference between the estimator and the truth behaves like a sample average of IID mean zero transformations of your data, plus some tiny negligible remainder term. Because we have this representation, then by the central limit theorem, we have normality, and also we have unbiasedness of our goodness and fit estimator. So now that we have this thing, then, as I said before, we estimate theta naught and theta star by taking the empirical minimizer of our estimator over the full and reduced class, and we just set cyan, the plugin estimator, as being the difference between the goodness and fit over the full and reduced class.
It should be GN, right?
That is a typo. Yes, that should be GN. Thank you. So a key result that makes this approach work really well is that the estimators GN of theta n and GN of theta star in n behave really similarly to GN of theta 0 and GN of theta star of 0. So in other words, it behaves similarly as if we'd already known theta naught and theta star to begin with. So the error of estimating theta naught and theta star goes away, sort of. So using this fact and skipping over a few details, then we're able to have the representation that the difference between cyan and theta and psi 0, which is the difference between the goodness and fit estimators over the full and reduced class, can be expressed as a difference in sample averages plus a tiny remainder. Because differences of averages are also averages, then we also have a central limit theorem for this estimator. And so now we'll see what this does and does not do well. So first, we're going to consider how this plugin estimator works when the alternative holds. So this is the case when the improvement in fit is bounded away from 0. And so the central limit theorem implies their estimator is going to be in large samples, approximately normally distributed, with mean at the truth, and with some variance that's decreasing at an n rate. And so in this case, our estimator is behaving as advertised. It's asymptotically normal, just like we would want. However, something funny happens when the null holds, right? So we're claiming that our estimator is going to be asymptotically normal with mean centered at the truth. But in this case, under null, the truth is 0. So if it were mean 0, so if our estimator was asymptotically normal, that would mean half the time it would take values outside of the parameter space. Clearly, that's not possible, and that doesn't make much sense because our target of inference size 0 is non-negative, and also our estimator is also constructed to be non-negative. So the normal approximation is failing. And I haven't lied to you about our estimator having this representation as a sample average. But what happens is that the leading term in the sample average vanishes. Okay. So under the null, theta naught and theta star are going to be equal to one another. And so that means that this leading term in our sample average is going to vanish because these two terms are exactly equal to one another. So under the null, the leading term is 0, again, because we have equality. And the convergence rate and the sampling distribution are now determined by the tiny remainder term. And the tiny remainder term, while small, is really formidable and it gives us problems. It has a very complex sampling distribution that's difficult for us to understand. So now inference becomes really difficult. Okay, so it's helpful here to talk a little bit about convergence rates. So what the central limit theorem tells us is that under the alternative, the plugin estimator is converging at a root n rate. And we're also able to establish efficiency, so we're achieving the minimum variance among all root n consistent estimators, which is great. However, under the null, we're finding that the convergence rate is faster. And so my intuition for why this happens is that we have sort of two contributions for what's affecting the convergence rate. First, we have a root n rate because our goodness of fit estimators are asymptotically linear, or they behave like sample average, so we have central limit theorem on those. And then we're getting an extra contribution. We're getting that the convergence rate is speeding up a little bit because our estimators theta n and theta star n, they're converging to the same quantity under the null. So now we have one thing that's converging at a root n rate, and we have another thing that's converging a little bit faster than root n, and you end up sort of multiplying the two together, so you get this slightly faster convergence rate. And you usually get a convergence rate that's somewhere between n rate and root n rate. And a lot of the time we say that's fast, but actually it turns out to not quite be fast enough for us to be able to perform inference. So we need to do a little bit better. And so this is a general problem that we find when we try to construct non-parametric estimators for functions that take the form of non-negative similarity measures. It's been a pretty open problem in the field for a while. So in parametric problems, when the null holds, we have nice behavior in that our estimator behaves like a squared sample average at the boundary of the parameter space. And so because of this, we still get central limit theorems and continuous mapping theorems, and we get n rate convergence. So this is where chi-square distributions come from, right? When something behaves like a sample average squared. And so again, to reiterate parametric problems, we'll still get a root n rate away from the boundary, but now we're going to get an n rate at the boundary. And so I think what the open problem has been is parametric rate inference achievable in non-parametric models? And I found that a lot of the times, yes, under some assumptions. And so in what follows, I'm going to reformulate the problem in a way that's helpful and that allows us to understand exactly what the plugin estimator has done wrong and what can be done about it. And so I'm going to explain this in 3 different ways, first in words, then in an example, and then in pictures. And so this is a great place to stop me to ask questions because I think that this is key for understanding why I'm doing what I'm doing. And so estimating an improvement in fit, I like to think of it as really as you want to perform a search away from the best null fit to identify whether there exists something better in the difference between the full and the reduced classes. So you're performing a search away from theta 0 star to see if there's anything in the place where we haven't looked yet, and the difference between the full and reduced class to see if there's anything there that might be better. Okay. And so I'll begin to think about a way to characterize this class in a way that's helpful. So first, I'm going to say that we'll say that we're going to fix any arbitrary function f and we'll fix some constant equal to beta. And we're going to, using these two, we'll consider a simple submodel, a parametric submodel that's indexed by a single parameter beta that is passing through the null parameter at 0. And here we'll denote this by theta star of 0 and f. And we're assuming that theta star 0 and f is equal to theta star 0 when beta is equal to 0. And so we're going to say that we can have any one such submodel, and we can also think about getting more and more functions f. So we can now start to get a collection of parametric submodels. But any one of the individual parametric submodels is nice. And so we're going to assume that we can represent the difference between the full and reduced class as being the collection of these parametric submodels. So you have one submodel for every f, and then you're looking over the parametric submodels over beta over the real line, but they're indexed by these functions f. Please. So f isn't necessarily a density. So f is just, so we'll see an example in a second, in a moment, what f could be. Pardon? Yeah, f is basically a direction. So you can think of this as being an element of your tangent space. But yeah, it's a direction that is passing through the null parameter.
And beta is the parameterization of that.
Yeah, so exactly. So f is a path and beta is the direction along the path, or beta is a location along the path. Exactly. Yeah. Oh yeah, that was me being too terse. So I'm assuming equality to the null. So we're assuming that theta star of 0 and f is equal to theta star 0. So it passes through the null at 0. Yeah. Great. Other clarifying questions? Great. So now that we have this collection of submodels, we can now think about identifying what the best fit along any submodel is. So now we'll say again that we fix an f, and we're looking along this path f, and we're taking whatever the best location is along the path. So what location beta is giving us the minimum of the goodness of fit along this path. And then along this path, we can think about defining an improvement in fit just along the path. So looking again along that path, what is the goodness of fit at 0? And now what is the goodness of fit at beta 0 and f? So how well can we do if we just considered a simple parametric submodel? So now we can repeat this again over every different submodel within our class, and we get a collection of different improvement in fit parameters. And now we can have the representation that our global improvement in fit psi is equal to the maximum of the little improvements in fit little psi f. So we can think, yeah. Oh, that's the beta 0 f. Exactly. Yeah, and that's important. Yeah, so the best fit is going to be non-negative. Some fits may be worse along a parametric model. So yeah, that's a good point. Thank you. Yeah, so you do that along every submodel. So first you get the best along every submodel, and then you take the best of the best improvements in fit, and that gives you the global quantity. So, just a quick example. So briefly revisiting the regression problem. So again, we're interested in comparing a full regression model that depended on both W and X with a reduced regression model that just depends on W. And so you know that the null best fit is equal to the conditional mean of Y just given the adjustments W. So you can think about defining your submodel as just being the sum of the conditional mean of Y just given W plus some constant beta times some fixed function that takes as input both the predictor, both X and W, but of course would have to change in would have to depend in some way on X. And so now we're basically fitting a linear model sort of. So now there's one parameter that we're interested in beta, and we're basically want to see whether beta is helpful. So is beta equal to 0 along the submodel is the best fit along this linear model with beta is equal to 0. And so you can then repeat this for many different choices of f, and then you just take identify what submodel is reducing the predictive error, the prediction error the most along all such submodels. And you can find that the best F, so the one that's minimizing the goodness of fit, is proportional to the difference between the truth and the null. So proportional difference between the full conditional mean and the reduced conditional mean. And so those were two words explanations, but I think it's also helpful, at least for me, to have sort of a geometrical picture in my line. And so in this photo, so first I'm going to represent in this rounded rectangle is going to be our difference between our truth and our null, our full and reduced model classes. So this is sort of this function space that we're looking over. And in a moment, I'm going to plot contours of the goodness of fit along the set. And so I'll represent darker values are going to represent worse fit, and lighter values are going to represent a better fit. So now I'm considering what this goodness of fit or what this risk surface might look like under the null. So I'm plotting in the center. The center is the null best fit theta star. And here I'm showing that the risk is not minimized at theta star. So theta star is in the center, but it looks like the risk is minimized somewhere in the bottom left corner. Okay. So now I would draw a fixed submodel F, which is just going to be, in this case, a straight line that's passing through theta star. And we can think about plotting the goodness of fit along this path theta star. So the place where we're passing through the null is at the center, that's 0, so that's the vertical gray line. And the minimum along this parametric submodel, I'm indicating by the vertical orange line, is going to be at -1. And so the improvement in fit along the parametric submodel then is just going to be the difference between the best fit, which is at -1, and then the null fit, which is at 0. So there is going to exist a least favorable path, which is the path that's going to draw from the null towards theta 0. So that's going to be the place where you're getting the biggest change in the goodness of fit. So what the plugin estimator essentially does is it says that, well, we want to get inference along this path, basically. So what we do is then we supply an estimator for this least favorable model. And we try to perform inference just along this least favorable model. And that turns out to work pretty well. So asymptotically, under the alternative, there's no consequence due to having needed to estimate the least favorable path. So the estimation error ends up not contributing anything asymptotically. And that's the big idea that targeted learning and one-step estimation are basically using. But under the null, things get a little bit tricky because now under the null, there is no least favorable path, right? So any path that passes through the null is achieving its minimum at the null because the null is minimizing the goodness of fit. So to think of this as, in this case, all submodels are technically correct, but none are actually helpful because none are helping you achieve the goodness of fit, but all are correct that beta is equal to 0. And now we can think about what is happening with the plugin estimator and what is the source of its sort of wonky behavior. And a few things. So the first thing is that the plugin estimator for the least favorable model might not even necessarily be converging to a fixed model because the least favorable model isn't well defined anymore. So now you can just have something that's like pointing in any random direction. And so now we have this empirical best model is now random, and we don't really have a good sense necessarily of how it's being selected, especially given how we might be using really flexible, complicated strategies to be estimating the least favorable submodel if we're doing it in a non-parametric model. So that's problem number 1. But also, as we noted, any different model within our class, since all of them were just as good of a job at the population level, any can potentially win out and have the empirical best performance. Okay. So because of this, the behavior of the improvement in fit estimator is now depending on not just how well we're fitting along the least favorable model, but how well we're fitting along any of them, because any one of them can potentially be winning out. And so we potentially might not be getting efficient inference along each of these different submodels that are passing through the null. And the reason for that is because the null best fit, the fact that we needed to estimate it actually is introducing bias. It's really sneaky bias because it's converging at a rate between n to 1 over n to the 1/2 and n. But it's introducing bias that only shows up at the boundary of the parameter space, and it actually does not show up when we're away from the boundary of the parameter space. And so in summary, so the one-step estimator, or sort of the plugin estimator that we've been considering before, it's taking a shortcut by only trying to do inference along the least favorable path. And normally this is fine, but under the null, we're losing efficiency as a consequence, because we need to make sure that we're getting inference along all the different paths. So as an aside, and something I think is really interesting is, as I mentioned, so non-parametric estimators like target maximum light or target minimum loss weights estimators and one-step estimators are really predicated on the idea that taking this kind of shortcut is okay. You don't pay any consequence for it asymptotically. But this is an interesting case where that's not okay, and you actually pay a pretty big loss in efficiency. And so I'm here, I'm talking about rates. So you're getting, so you're getting a suboptimal rate, yeah. And so then from this setup, and this is going to be the 5 slides where I talk about what I do, is to get a new estimator. It's reasonably straightforward, is that we just stop taking shortcuts. So we instead construct an estimator taking the scenic route, is what I'll call it. And so we can think about this in 3 steps. So step 1, we efficiently estimate the best fit along each different submodel. And we have ways for doing this. Again, the usual target maximum likelihood, whatever you want, is going to work there. Second, you estimate the goodness of fit along each of these submodels. And then you take your new estimator as being the maximum of the improvement of fit along any of these paths. So easy as 1, 2, 3. And so this relates really well with parametric inference. And so when we do a really good job of estimating the goodness and fit along any path that's going through the null, then our estimator for the goodness of fit is behaving a lot like the log likelihood. And so that means that the minimizer, so the best fit along any different submodel, is going to behave a lot like a maximum likelihood estimator. And because of this, the improvement in fits, the difference in goodness of fit along the null and best fits along any path is going to behave like likelihood ratio statistic. And likelihood ratio statistics converge at an end rate. So this seems promising. So very briefly, I'll bring us back to the regression problem and just talk a little bit about what's required there. I'm not going to go into a ton of details because it just gets a little bit technical. But recall that we had the model that we're drawing any parametric submodel as being equal to the conditional mean just given the adjustment variables plus plus beta times any fixed function of both the predictors and the adjustments. And assessing whether something has improvement fit is determining whether beta is equal to 0 for any of these different submodels, so any of these submodels help at all. And so for folks who've seen partially linear models, these are models where you have basically an intercept that's flexible that can depend on W that you need to estimate using machine learning techniques, which will be this part, plus a simple linear predictor of usually just of X, but here it can be a linear predictor of X and W. We have sort of this flexible flexible function here, and then you have this fixed thing here, and your parameter of interest is just this coefficient beta. And so basically what you do in this problem is you just fit several partially linear models for several different choices of F. And in these sorts of problems, in regression problems always, if you want efficient inference, then that requires you to know 2 things. So you need to know how the outcome depends on the exposures or on the adjustments in this case. You also need to know how the predictor of interest, which in this case is F of X and W, how that is also depending on the adjustments. Right. And the second part is really important, and it's something that sort of previous methods of variable importance were missing. And it's actually the source of our getting bias. But this is something that always comes up in regression problems. That's why in OLS regression, we need to estimate this X transpose X inverse, this covariance of the predictors, or why you need to estimate why you need to estimate the inverse of the Fisher information in GLMs. It's because of this. So if you're not doing this, you're probably not efficient. It's sort of my rule of thumb. And so I'll only give 2 slides on theoretical properties because I think they're somewhat intuitive. So first, we have that one of the null holds, our estimator is converging at an n rate and it has a nice sampling distribution. I won't go into how we characterize that sampling distribution, but it's nice enough. So it can be looked at basically as being the maximum of many different squared sample averages that are correlated with one another. So it looks kind of like a chi-square distribution. And we have methods for approximating the null limiting distribution using something like a bootstrap or a Gaussian approximation, or whatever. And so this makes hypothesis testing fairly straightforward. At that point, it becomes more of a computational exercise, but we have nice theorems that say the null is that the null limit is available. And so then we can ask, well, we knew that the original plugin that we were considering is efficient, and then we can think, well, is this estimator also efficient? And the answer is yes. So our estimator is asymptotically normal and sufficient when the improvement in fit is away from the boundary of the parameter space. So in particular, we have an asymptotically normal estimator for the best improvement in fit along any path in our function class F. And the reason I stated it this way is because your function class can technically be misspecified and you still get this normality result, right? So in the previous example, we were saying that, oh, we're trying to get this sort of difference in the conditional mean using full and reduced covariate or in the reduced models. Well, we might say that we want to use a simpler model for the difference in the conditional means, or maybe your model is too smooth, or maybe we've missed something. Well, we have a result that tells us that even if we have the model that's misspecified, we still have an asymptotically normal estimator for whatever the best thing in our model was. And so we have this sort of nice robustness result here, and I don't know whether that's available for the plugin yet, but I think that this is nice, and it's a quantity that we're able to precisely define, and often it can be somewhat intuitive. And so just a brief comment on the choice of a different function class. And so we're using our function class script F as being a model for the difference between the true parameter and the null parameter. So basically we're trying to find out what direction is pointing towards the truth. And this class, it doesn't have to be a parametric class, but it can be a really flexible class as long as it doesn't, it satisfies some complexity constraints. So this can be like a class of smooth functions or a class of functions with bound derivatives or anything like that. Or in many settings, it's reasonable. Say in causal inference problems, we expect that functions are monotone. So it can often be reasonable to say that our function class is a class of monotone functions, and that also has enough structure to be A-okay. But I think the bottom line here is that we can incorporate all of the structure that we know about our problem into our function class script F in order to potentially get more power. So that gets us into thinking about, I don't want to say structure constrained, but structure supported in statistical inference, which is a new and useful idea that I'm interested in further investigating. And so I'll talk about a bit of an illustration and sort of connect with the talk that I gave yesterday at Hutch, if anybody is tuning in. And I'll talk about a few simulations and then start to wrap up. I don't even know how I'm doing on time. Okay. Yeah, so yesterday I talked about how this framework can be used to perform inference in a regression or causal inference problem, depending on who you ask. And so we're going to find as our target of inference to be just if we had a conditional mean function, so the conditional mean of an outcome given x and w, taking the average of that conditional mean function marginally over the distribution of the covariates. So under causal assumptions, this can be represented as being sort of a measure of the effect of our predictor x on y, adjusting for w, but in general, it can just be thought of as being a measure of the conditional association between the outcome and x given w. So if x is univariate or variate, then this can sort of be just like a nice summary of our conditional mean function. And one thing that we might want to know is this function flat? So is it taking the same value for every different value of x, which sort of gives a different notion of how important x is. And so we'll say that our full function class is just going to be all functions of the predictor. And we'll say that our reduced function class now is all constant functions because we want to know if this is flat. So can we say that this function is equal to a constant function? So now we're going to, in this case, one inference on a dissimilarity measure that just using sort of an naive approach, I'm going to say is just an integrated squared difference between the truth and its expectation. So this is basically measuring the variance of something. If the variance is constant, then that means it's 0 or flat. So this is a reasonable measure. And so I implemented this approach. So in a different paper, I looked at this problem extensively. And here I'm going to look at, so using this framework and developing a test, and again, skipping over some technical details because they're sort of away from getting to the main point. I'm just going to look at, so if you use our approach, how well do we do in terms of type 1 error control? How well do we do for power into the alternative? And what do the sampling distribution of our estimator take? So are they having the behavior that I claim that they should have? And I'm going to just consider a simple setting. We don't have very many confounders. So I think it was actually a 2-dimensional confounder here. And I'm going to consider 2 different choices for our function class script f. So one is going to be where f is constructed data adaptively, but without sample splitting. So we're cheating and we're seeing how much we pay as consequences of cheating. And a second where we're picking it as an oracle function. So we're going to say that we have, we're considering a class of smooth functions, and we'll define the oracle as the smoothest function, or the smoothest function class that still contains the truth. And we'll compare by a method that was proposed by a different University of Washington alum, Ted Wessling, who was looking at the same problem, but formulating it as sort of a Kamal-Grosmirnov test. The difference between these 2 approaches isn't essential. You can ask me about that later. So getting into results. So I used 2 different types of estimators also, by the way. So I used a one-step estimator and a targeted maximum likelihood estimator. There are no meaningful differences between the 2. And we find that we actually get reasonable type 1 error control. So in these plots, I'm showing on the x-axis, the nominal type 1 error level, and on the y-axis, I'm showing the reduction probability for 5 different choices of methods for 5 different varying sample sizes. So everything is working. If we're getting proper type 1 error control, then all of these curves should really hug the 45-degree line. And we're finding out that we're doing pretty well. We get some like modest type 1 error inflation, and this can be attributable to a lot of things, just like estimating nuisances is hard. So in this problem, we need to estimate conditional density functions, and conditional density functions are really hard to estimate. And so it might just be a consequence of that. And so then we look at the power of our proposal, and I guess sort of the ranking. So we find that all the different approaches that we consider are actually fairly well powered. And there is a sort of hierarchy in terms of power. So first we find that our approach, when you're trying to adaptively learn the smoothness, well, moderately powered is the worst among the that we're considering. You do the best when you know the power a priori, and this sort of Kamal-Grosmirnov approach, where we're specifying things, but not necessarily has other disadvantages, is sort of in the middle of the 2, but I'll perform pretty well. And last, I'll look at how the limiting distribution of our proposed estimator for the improvement in fit, first considering the null, and then considering the alternative. So in this plot, I'm looking at the sampling distribution with increasing n, where I have not scaled the sampling distribution by the sample size yet. So what we should find, because we haven't scaled things, that as the sample size grows, we should have that our estimator is getting closer and closer to 0, was what we're finding. And now if everything is working, then once we multiply this by n, we should find that the sampling distribution is basically the same for all the different plots, because we should have the things are stable once we multiply by n. And everything works as advertised. So now we're finding that we're able to get the limiting distribution correctly, and it is having the claimed convergence rate. So second, we look at the alternative, and we should find similar behavior. So I centered things by mean 0 because otherwise making comparisons is a little bit weird. But we're finding that first, again, when I've not scaled the sampling distribution by n, we're finding that things are approximately normal, and the standard error is decreasing with the sample size, and this conversion is 0 eventually. And then under the alternative, when I scale things by root n as I should, then the sampling distribution is pretty stable, and the variance is not changing anymore. So everything is working as advertised. And so that's it for main results. And so I'll just end a little bit with a summary of my contributions, and then a brief discussion of where I might want to go with this work in the future. And so I started out by arguing that non-negative dissimilarity measures are really useful, and in particular, they're useful for constructing omnibus tests. So if you want to construct a hypothesis test that's going to be powerful against any different possible alternative, the most natural approach is to define some similarity measure that's looking like this, something that's a measure of distance, essentially, between the truth and the null. And so this has been an active area of interest, both sort of recently in folks looking at regression problems, but also really classically for decades, people have wondered, how do you get inference on things like mutual information, so omnibus test of conditional or of marginal independence? And we have not been able to get rate optimal tests out of that so far as I've seen. And so then I spent a really long time unpacking so why the current state of the art fails, and then using that sort of once we got an idea of why things were failing, then we're able to propose a general strategy that was, I don't want to say simple, but somewhat intuitive in light of the problems that we had with the current state of the art. And so I remain really excited about this work. So I've been thinking about similar problems for like 4 years or so now. And I probably am going to continue working for a while because it's like the Hydra. Every time I feel like I figure out a problem, then 3 more pop up. So there's a lot of things to do on many fronts. So actually my first order of business is I think at this point, I understand the problem well enough that I can think a lot about implementation. So I'm going to step away from math and I think spend a lot of time coding as soon as I get this paper out. So really, I want really good software that's treating canonical problems, so things like regression problems. So I really would like a treatment of something like non-parametric generalized linear models in this framework. So something that's stable and runs and gets inference and is reliable. And we really sort of think a lot about these practical considerations like tuning parameter selection, and that in these theory papers, I'd sort of been glossing over, but really need a lot more consideration if this is going to get used. So that is first order business. Second, which I also would like to do concurrently, is just thinking about applications. So I'm interested in what kind of applications other folks are interested in, but me working at the Hutch, so I work a lot in vaccine efficacy trials, and I'm thinking about ways that this can be useful for different problems that arise. So thinking about things that are correlated with risk of infectious disease outcomes, or things that are associated with protection of vaccines to risk of infection, or things like that. So when these methods are useful there and how they should be adapted. And I think that there's a lot to be done on the theoretical front as well. And so one thing that I'm interested in, and for folks who were in my talk yesterday, is I'm really interested in thinking about constructing confidence intervals for parameters like theta naught using these sort of test inversion based approaches. And I'm wondering what sorts of advantages there might be. Please. All right, the screen went blank, so I don't know. And so I'm interested in thinking about what advantages might be, especially now that I noted that we have approaches now for incorporating structural constraints or structural assumptions about our parameter of interest into our hypothesis test. So can we think about getting sort of super efficient hypothesis tests, even when we've always had super efficient estimators, but now can we think about how can we beat efficiency bounds on hypothesis tests using some of these ideas? Second, I'm interested in getting sort of a more thorough theoretical or understanding theoretical properties, or really I'm interested in somebody else working that out. But I think that it's important for us to understand how these ideas are relating to other different approaches. And so I think that this is like a great first stab at the problem, but I think that this problem is fundamental enough that even just for like pedagogical purposes, I would like to see us sort of slowly get towards a textbook level understanding of the problem. So I think that there's more things that need to be written about. Like how does the complexity of our function class impact power, and things like optimality, et cetera. So I think like this is a great start, and this means that we can solve the problem, but I think that it's helpful, if not for practical reasons, just for pedagogical reasons, to understand why do things work. And third, so I described that sort of, I have this approach for estimating by taking a so-called scenic route. So I said that there's one way you can cheat when you're trying to sort of get inference on this improvement and fit by just estimating the least favorable model and then getting inference on that thing, and that there can be some advantages, at least in this case, to not estimating that directly, instead saying you want to get efficient inference on all the models and then take the best. So I'm wondering, well, that's helpful in this problem. So in this place where we have these boundary null issues, but I'm wondering in what circumstances that can also be helpful. So does this give us, say, better finite sample properties when we're interested in other canonical problems, things like estimating average treatment effect? I'm using non-parametric approaches. So I don't know what'll happen there, but I'm curious. Yeah, and so I think it might be, I can stop there. That's all the material I have, and I'm happy to take questions.
Right, any questions either online or here? Yeah.
Thank you. Yeah, I'm trying to figure out how you can actually do that efficiently. So taking the scenic route. So there's things that you can do to make it computationally faster. Right, so I talked about basically when you're performing inference along parametric submodels. And I said that one way to do that is by getting an estimator for the goodness of fit along every different thing along the path. So you can from wall test or likelihood ratio test basically. Well, score tests are nice. And score tests sort of circumvent that problem. So you reduce the number of different things that you have to estimate because now you only have to, so a score test works as you're looking whether that function is maximized at the null by taking a derivative of the goodness of fit along that path at the null. And so now you've reduced the number of things that you need to estimate. And that turns out to be actually pretty manageable. So figuring out like when will this make sense for like ratio statistics and things like that. It can be done, but it's like, it's a pain.
Any other questions?
Yeah. So your simulations,
Mhm.
You see that you have, half a normal, basically.
Yeah.
So that tells me that you were showing all the simulations at the alternative, and an alternative that was far away from the null, enough away from the null, that was truly normal. But now if I wanted to go to construct like a confidence interval, on those, because now the distribution doesn't converge uniformly. So I guess can you comment on that?
Yeah, so that's a great question. And so I don't know if folks online can hear. So the question was, so let's say we want confidence intervals for the improvement in fit. So let's say it's a parameter that's just of independent scientific interest. So we're not satisfied with an estimate in the p-value and a confidence interval. And so getting a confidence interval can be difficult because usually we get a confidence interval by using a normal approximation of the sampling distribution, but that only works sometimes. So away from the boundary, that works. At the boundary, we're getting this half normal thing, and then in the middle, we're getting something different. And so my answer is, it's absolutely possible, but I've given up on it for computational reasons. So the way to do it would be by inverting a hypothesis test. So you would characterize what the sampling distribution for the improvement in fit estimator would be under any different null. So you can do that at the boundary, and you can do that away from the boundary. And I know what your concern is going to be. Well, it's going to behave something different than that near the boundary. Exactly. So you can learn what that sampling distribution would be near the boundary. However, it's still really complicated. So there's a lot of different sampling distributions that it could take, depending on sort of the distribution of how well you're doing along each path, right? So there's a lot of different configurations of the improvement in fit along each path that can give you the same global improvement in fit. So in the boundary, what you want to do is you want to be able to say, to reject the null that size 0 is equal to some number that's really close to the boundary, you would want to be able to reject the null at every different one of those configurations for the little improvements in fit. And that just ends up being really computationally intensive. So like theoretically possible, but I haven't figured out a way to do it cleanly.
Just from a very abstract, general point of view, you have a parameter that it's simulated, right? Because at the null, at a particular value, it's easier to estimate than at some other. So somehow you have to be adapting the null distribution at which you test when you invert the test.
Exactly.
Not just use
Yeah. Yeah.
That is adapted.
Right. So the way that, and what helps us do that is we can characterize the local alternative distribution. So that sort of gives us a sliding scale that lets us look at, well, when we're really close to the null, what happens, and we're away from the null, and what also happens. So the right way to do it would be to look at the local alternative distribution It's just that that's impossible to estimate. So then you would have to like do this thing of inverting around the local alternative distributions, and you get into this sort of intractable, computationally intractable problem. So you're entirely right. Totally important in a lot of settings. Also absolutely possible, but I've thrown it in the towel. I tried to do it and just couldn't.
It's very much related. There are many issues, and you are referring to, estimation on the boundaries. I mean, on the boundary constraints, it's always this kind of balance. And also, when you have parameterizations where a parameter, in parametric model, the parameter is identified as some particular value, the information matrix is singular, but the weight on that is not. You kind of have the opposite, because at that parameter value, you have slower rates of complexity. But it's again, it's a method to do confidence. Anyways.
Yeah, no, thank you.
Any other questions?
Yeah, so looking at the data.
Yeah.
One thing I like with the framing of market makes is thinking about the ideal observable data and then the actual observable data. And so the ideal observable data is more or less to be focused on using the deal with like risk and data.
Yeah, thanks, Peter. So for folks that didn't get online, so I focused on like a really simple setting here when we have IID data, but a lot of the times it's actually data that we'll observe in practice, especially data at the Hutch will have other kinds of problems, so missingness or competing risks or censoring or other such things. And yeah, I'm interested in doing that slowly. So I barely understand the IID problem yet, so just trying to make things easier for myself with starting there. But I think one of the next things that I'm interested in doing is just moving a little bit further and thinking about right censoring. Since that comes up often and there are important, but also like fairly clean right censored data problems. And I'm interested in like addressing additional layers of complexity. But I think I'm interested in doing that slowly. I think I just want to make, and I think I understand like the basic problem well-ish enough now that I can maybe start thinking about that. But I wanted to make sure that first is, well, what do we even do with IID data first? And then we can think about, so what changes? And I think that things should probably change pretty nicely. Everything work, you just need to set up usual asymptotic pair, so set up estimating equations or set up whatever, and everything still works. But just like sort of dealing with that nuances, dealing with those nuances, yeah, I would like to do that. I'm slow.
Any other questions? Not then, let's thank Aaron again.